बिस्मिल्लाहिर्रहमानिर्रहीम। सागर में तेरे साकी दिल का सुकून देखा, ला खौफ आज खुद को ला यह जनून देखा. My dear students, I hope that you all will be safe and sound. So today I am going to talk about Schrodinger wave equation. So before going to drive Schrodinger wave equation, I would talk about the introduction of Schrodinger wave equation. As we are learning three models of atom since early education. First of all, J.J. Thomson gave the idea of plum pudding model, and then Rutherford gave the model of atom, and third idea of atom was given by Bohr. Actually, these all are the model of particle nature, in which we all assume to these subatomic particles as a particle nature. The electron, being a particle, revolves around the nucleus, which we knew in all the models, but in these all models there were some limitations. Actually, these all models were valid until the hypothesis of de Broglie came, and until de Broglie gave the concept of matter wave, these models were we can say valid. These all were about the model of atoms. So now I am going to touch the case of light. First of all, corpuscular theory told us that light is a particle that behaves like a particle. After that, Heisenberg theory told us that light has a wave nature. Its confirmation was given to us by the experiment of young double slit. After that, we knew that light has a dual nature. Actually, light travels in the form of discrete packets of energy, which we call photons. And further, de Broglie worked on it and said that light is an electromagnetic wave, so therefore it should be applicable in all the cases of electromagnetic wave. And this thing told to Einstein, and Einstein replied that why are you thinking only in the case of electromagnetic wave? Apply it to whole the case of matter. And from there, de Broglie gave the hypothesis of de Broglie, in which he told when matter moves, it moves in a wave form, which we call matter wave. And when we move, a wave generates around us, which we call matter wave. But the question arises that why we can't see these waves? Because the wavelength of this wave is too short. It means that the wavelength of the greater mass is short. But when we go to, in the case of atomic particle, like the case of electron, in which wave of matter become applicable, and wavelength become more, so we can't neglect it. We got the confirmation of matter wave from the alternate version of young double slit experiment, where we fired electron instead of light, and in that case we saw interference fringes. But if we do not observe the electron, then it shows wave nature. But when we observe the electron, it shows the particle nature and does not show the interference fringes. In this all discussion, we know that the electron revolves around the nucleus in the form of a wave. However, previous models of atom told that electron revolves around the nucleus in the form of particle. But actually, electron revolves around the nucleus in the form of waves. But we ask why? Because it is so small. And in this case, de Broglie wavelength become applicable. But in order to show the wave nature, we have faced some difficulties. What they are? First of all, we cannot tell the exact position of electron in wave nature. So consider this is a wave of electron. So what is the position of electron in this wave? We are not able to identify the fixed position of electron, because if we say the electron is present in the upper side of wavelength, which I have drawn here, so the question will arise that is it complete wave? This electron can be present in the lower side of wavelength, which I have drawn line below. It means we are not confirmed yet, so here is uncertainty. So that's why Heisenberg uncertainty principle become applicable. And second difficulty we felt that how this wave of electron is made up of. So until the answer of this question is not found by the we can say scientist. Here somehow we discuss one thing of classical physics. Suppose this is a football and its weight is 1 kg and we apply 2 Newton force on it. Can we find its acceleration? Yes, we can find out its acceleration because we know that F is equal to ma. With the help of this formula we can find out its acceleration. And can we find out its velocity? Yes, obviously we can find out because acceleration is equal to the change in velocity with respect to time. So from dv upon dt we can find out the velocity. We can also find out the position through dt square x upon dt square. Here in formula d square r, but we can write both, either r or x for position. If we know the mass and velocity of any object, then we can find out its energy. It means that with the help of this simple equation we can know all the things of particle. But when we take this classical equation to quantum level, in this case this classical equation does not work. It means this is not valid there. So Schrodinger equation was given against the equation of F is equal to ma, which is applicable in quantum level, which we call Schrodinger wave equation, and that is Schrodinger wave equation. So in this equation there's a psi which I have represented with blue line, and this psi shows the wave function. What the wave function is, this I have explained in next slide with graph. And here partial derivative of x square, y square and z square shows the position of electron in 3 dimension, and m represents the mass, h represents the Planck's constant. The value of h is 6.626 into 10 power minus 34 joule second, and E represents the total energy and V represents the potential energy. We know the value of mass, so we can find out the velocity. It means that we can find out the kinetic energy. It means with the help of Schrodinger wave equation we can get the knowledge of all the things of atomic particle. As I told you in previous slide that I have explained the wave function in next slide. So here I am going to discuss about the wave function. First of all, we see its definition. Wave function in quantum mechanics, variable quantum that mathematically describes that wave characteristics of a particle. Okay, so we understand the wave function with the help of graph. This is the graph of wave function, where the peak of wave is high, so there is lot of chance to gain electrons. See the line which I have drawn, which is in high peak. So we can say that there is lot of chance to gain electrons, means where the value of psi is greater, over there the chances of electron is greater. If we see the lower peak, we see negative value, means that upper value is positive and lower value of peak is negative. Do the chances negative? No, because probability cannot be negative. It means that this psi has no physical significance. Same as the negative sign under the under root cannot be possible. Later on, scientists thought that psi has no any physical significance, but if we square it, now square has physical significance. Psi square tells us probability in order to find out the electron. This tells us the chances of electron, that here we get the electron. It means that this probability tells us probability density factor. When we put the value of hydrogen in this equation, we will see the wave function of hydrogen, which will be in the shape of orbital. If we take one atom and give the energy to electron, so that it revolves on third orbital, and measure its position. As we measure its position, its wave function will collapse. We find the position of electron, but its wave function has collapsed. If we do this process again and again and get observation, then we will get a shape of orbital. A shape is seen by us that the electrons are present in that place, but can't tell the exact position. You may understand that we are finding the position of electron again and again, and we are getting new position every time. When we do the calculation of these, then we will see a shape which we call orbital, where number of the chances of electron we can say are more. So with the help of this equation, we will get the knowledge of the orbital of the electron. Schrodinger gave us the new model of atom, which is called wave mechanical model, or we can say quantum mechanical model of the atom. He told us electron revolves around the nucleus in a cloud form, in which the position of electron depends upon its probability function. Where the probability function is 0, over there we will not get the chance of electron, but where the probability function is high, over there are many chances of the electrons. Okay, it was the introduction of Schrodinger wave equation. Now I will tell you the derivation of this equation. Inshallah you will get it. So first we have to focus on this figure. In this figure, the point B is the center of atom, and the point P is the electron revolving around the center of B. We can say the distance from B to P is the amplitude of electron, and from point C to P, that is a function which we call psi. According to triangular law, PC upon PB is equal to psi over A, and that will be equal to sine theta. By cross multiplication, A will be right hand side and psi will be equal to A sine theta. Remember that theta is equal to omega t, where omega is angular velocity of electron and t is time. So we will get psi is equal to A sine omega t, where omega is equal to 2 pi mu. So equation of psi will become psi is equal to A sine 2 pi mu t, which we say equation number 1, and it's continue in next. Here V is equal to lambda into mu, or mu is equal to V over lambda. So the function psi equal to A sine 2 pi V over lambda into t, and time can be calculated by the formula of position, that is x is equal to v into t. According to cross multiplication, t will equal to x over v. Now psi will equal to a sine 2 pi v over lambda into x over v. After cancelling v by cross multiplication, psi will equal to a sine 2 pi x over lambda, which we call equation number 2. Now by differentiating the equation number 1 and equation number 2 with respect to x, we get derivative of psi with respect to x will equal to a cos 2 pi x over lambda into 2 pi over lambda. It's continue in next slide. By arranging the equation, we get derivative of psi with respect to x is equal to pi over lambda a cos 2 pi x over lambda. Now again taking derivative of above equation, we get second order derivative of psi with respect to x is equal to 2 pi a upon lambda into sine 2 pi x over lambda into 2 pi over lambda. From basic we know the derivative of cos x is minus sine x and 2 pi x over lambda is an angle. So after the derivative of sine, the derivative of its angle 2 pi x over lambda will be 2 pi over lambda. After simplification, the second order of derivative of psi with respect to x is equal to minus 4 pi square over lambda square into a sine 2 pi x over lambda. Since a sine 2 pi x over lambda is equal to psi, so second order of derivative of psi with respect to x is equal to minus 4 pi square upon lambda square into psi. This is equation number 3. So this is the wave equation in one dimension. If we want to measure this wave equation in particle nature, then we further modify it and we put momentum in place of wavelength. So still it's continue in next slide. According to Planck's second order derivative of psi with respect to x is equal to minus 4 lambda square over h square. Replacing lambda by p, since lambda is equal to h upon p, or by squaring both sides, we get lambda square is equal to h square upon p square. So d square psi with respect to x is equal to minus 4 lambda square upon h square m square v square psi. This is equation number 4. Since p square is equal to m square v square, after simplification we get this equation number 4. Now taking right side in to the left side, it will become d square psi upon dx square plus 4 lambda square over h square into m square v square into psi is equal to 0. If we want to represent this term in energy form, as we know total energy of the particle is equal to kinetic energy and potential energy. Total energy is equal to kinetic energy plus potential energy. Now kinetic energy is equal to 1 upon 2 mv square and potential energy is equal to v, where v shows particle form of potential energy. By taking v into the right side, equation will be E minus v is equal to 1 upon 2 mv square. By cross multiplication, 2 into E minus v is equal to mv square. In next slides, by rearranging the equation, we get mv square is equal to 2 into e minus v, and v square is equal to 2 into e minus v upon m. Now we put this value of v in the equation number 4 and we get d square psi upon dx square plus 8 lambda square upon h square into m square into e minus v upon m into psi is equal to 0. After dividing m, we get d square psi upon dx square plus 8 lambda square upon h square into m into e minus v into psi is equal to 0. So this is the Schrodinger wave equation. By using this, we can calculate one dimension motion of particle. To calculate the motion of electron in space in coordinate in 3 dimension, we have this equation: d square psi upon dx square plus d square psi upon dy square plus d square psi upon dz square plus 8 lambda square into m upon h square into e minus v into psi is equal to 0. So this is for the calculation of the particle movement of electron in 3 dimension. These are the applications of Schrodinger wave equation. The Schrodinger equation is used to find the allowed energy levels of quantum mechanical system such as atoms or transistors. The associated wave function gives the probability of finding the particle at a certain position, and the solution to this equation is a wave that describes the quantum aspects of physics, and it is used in physics and most of chemistry to deal with problems about the atomic structure of matter, and it is an extremely powerful mathematical tool and the whole basis of wave mechanics. There is the time dependent equation used for describing progressive waves applicable to the motion of free particles, and last, the time independent form of this equation used for describing standing waves. Thank you.